In this video, we're going to look at the Ptolemaic and the Copernican models. The Ptolemaic model was a refinement of the early Greek models, and it was published in about AD 150 or so. It was the model that worked or was accepted for about the next 13 or 1400 years, so for quite a long time. The Copernican model is the model that succeeded the Ptolemaic model, at least in many scholars' minds. After this, we'll learn about more people's models, but we'll start with this one. For reminders, you may have watched the video that I made on the paths of the planets against the background stars. Here's the path of Mars back in July 2020 to about January 2021, so for about a 6-month period. And it would be the yellow line that starts over there to the right of the center, and then most of the time Mars will be moving from left to right against the background stars. That's toward the east, but every once in a while it does this weird little backwards loop, and it's hard to see that as a loop. If we were viewing this from a different angle, you'd be able to tell, but it does something like that. And the backwards part of it is called retrograde motion. Here's the path Mars will take from November 2026 to July 2027. The start of this in November 2026 would be up at this end, and for most of the time it's moving from west to east against the background stars, but then it reverses direction. Retrograde motion here, then it goes back to prograde motion, heading from west to east again. And so that is the motion of Mars against the background stars. It repeats its retrograde motion about every 2 years and 2 months, so about every 26 months or so, again and again. The other planets do this as well, sometimes in more complicated ways, especially for Mercury and Venus. Understanding and predicting this stuff was a big challenge for early models of the universe. This motion looks complicated, and it is. They had a couple of incentives. One was just understanding how the universe worked, and another reason for doing so was so that more accurate horoscopes could be cast by the early astronomers. Virtually all of them up through Galileo and Kepler were, let's see, Copernicus probably wasn't, but most of them were astrologers as well as being astronomers. So first, Claudius Ptolemy. We have no idea what he looked like, but this is a picture someone did hundreds of years after his death. Lived from about 85 to 165. We don't know for sure when he was born or when he died. He was the author of something that became known as Almagest, and that's a combination of Arabic and Greek. The Al is Arabic for the Magest is Greek for the majestic or majestic. It was talking about the majestic things in the heavens and their motions. But people also thought of the book itself as pretty majestic because it worked pretty well for a long time, as long as you didn't need to be closer than about 10 degrees to the actual position of something. 10 degrees on the night sky is about the width of your fist held at arm's length. In it, Ptolemy refined the geocentric model for better planetary predictions. Geocentric means Earth-centered. You'll see as soon as we look at Ptolemy's actual model that it was not actually Earth-centered. Earth was a little bit off-center, but things orbited the Earth more or less. Ptolemy was also known for a book on geography, mapping, and another on astrology. I'm guessing that is pronounced Tetrabiblos or something to that effect. So here's the Ptolemaic model. And this is a fairly simplified version of it, but it'll have the main features that we're concerned with. I'll show you a somewhat more complicated model here in a minute. If you can contain this model in your brain and describe it well, you'll have the hang of the Ptolemaic model. First of all, the Ptolemaic model was almost geocentric. The Earth was almost at the center. But if you look at the circles that are drawn for Mercury's orbit and Venus and the Sun and then Mars, Jupiter, and Saturn, you may start to notice that they're not exactly centered on Earth. The Sun had a circular orbit around a point near the Earth, and all of the planets had circular orbits around points near the Earth, and they all had epicycles. Epicycles are the small circles that are on the larger circles. The larger circles are called deferents, and the smaller circles are called epicycles. Venus and Mercury had interesting orbits. Both of them orbited points on a line between the Earth and the Sun. Now, the Earth stayed fixed in the middle of this thing. All of these things orbited around the Earth, turned around the Earth once a day, in fact, while continuing their motion along the deferents and the epicycles. Here's a more complete picture of what a planetary orbit would look like. Here's the Earth right there. This is the center of the larger circle here, which is the deferent. There's an equant point here, and I'll talk about that in a little bit. The planet itself is up here, and it moves around the epicycle circle at the same time that the epicycle circle is moving around the deferent. And so this is pretty complicated. The point marked center is the center of the deferent circle. That puts the deferent off center from the Earth, or eccentric is a way of describing that. And the epicycle is a small circle. The planet moves along that at constant speed, and that provides the appearance of retrograde motion. If you look up there at the epicycle circle, the point marked X, when the planet is there, it'll be moving on the epicycle in the same direction that the epicycle is moving on the deferent, and so the planet will appear to be moving in a counterclockwise circle around the Earth. But when the planet is down here at point Y, or near Y, it'll be going on the epicycle in a direction opposite the direction of the deferent. That motion can produce an appearance that the planet is moving backwards in space. Now, a complication tossed in here. From Earth's viewpoint, the epicycle does not move along the deferent at constant speed. This would be something you wouldn't actually try to produce an animation with this thing, or at least the ancient Greeks would not have done so. What they would do is have an equation that described the speed of the center of the epicycle moving along the deferent. They could calculate all this stuff. The equant is a point from which the center of the planet's epicycle appears to move with constant angular speed. So if you were standing there on the equant looking at the epicycle and you were able to see the center of the epicycle, that epicycle would move along the deferent in such a way that it looked to you like it was always moving at the same speed. To make things worse, each planet has to have its own deferent, its own epicycle, and its own equant. So that was the Ptolemaic model. Pretty complicated. We can look at a couple of animations that simulate things in the Ptolemaic model. Okay, here's the simulator. There are links to this in your textbook if you read the chapter section on this. This is the Ptolemaic model. Earth is the blue dot here. The gray dot is the center of the deferent, which is this circle. The green cross here is the equant, and then this circle is the epicycle. and then this red dot here represents Mars, and that's just the one that we'll happen to look at. And I'll start the animation. Oh, we need to back out here a little bit. We want to be able to see this zodiac strip down here, and the zodiac strip is where you'll be able to see the apparent motion of Mars against the background stars. And in this case, it actually is caused by Mars moving around this fixed Earth in the center. You can also see the apparent motion of the sun against the background stars. Now, one thing about this animation that isn't correct is that it has the sun outside of Mars. The sun in the Ptolemaic model would actually be inside the deferent for Mars, so it would have been inside this circle. But appearance-wise, this will produce exactly what the Ptolemaic model would show for a view. So let's start the animation. At times I'll slow this thing down, and so you can see something. So here's just what the model looks like. You can see Mars moving along that epicycle while the epicycle is moving along the deferent. And you can watch that for a couple turns here. And then down here on the zodiac strip, you can watch the sun moving against the background stars with pretty constant speed. You can have Mars moving against the background stars, but every once in a while it does something kind of weird. So I'm going to slow it way down the next time it starts getting close to the sun here. Mars is falling behind the sun by quite a bit, but it's reversing direction right now. It's doing its weird little thing on the epicycle. Now the sun's going to catch up to and pass Mars. Now Mars is going to be starting on that part of its epicycle where it's moving in toward the Earth, and it's when it's along this part that it looks like it's going backwards against the background stars. There, down here on the zodiac strip, you will soon see Mars stopping, reversing direction, and then going forward again. That is the retrograde motion that you could see for Mars. A simulation of that. Now there's one more thing that I want to show you with the Ptolemaic model, and that is the phases of Venus. Now at the time Ptolemy developed the model, the telescope was still, let's see, about 1,450 years in the future. They didn't have any idea that there might be phases of Venus. When Galileo came along, he could talk about the phases of Venus that would be predicted by the Ptolemaic model and compare them to what he actually saw in the sky. This time we're just looking at Venus, and here we do have the correct geometry. We have Earth here, Venus's deferent here, and Venus's epicycle here, and then the sun is outside of that. And if things aren't lined up just perfectly with Earth, Venus, and the sun, you can see a small crescent, extremely thin crescent along the right side of Venus there. So let's start the animation. And if you look at the bottom picture here, you can see it's weird. Venus is a growing crescent, and it always pauses before it gets to a half Venus and then disappears and goes back to a crescent on the opposite side. This is what the Ptolemaic model would predict if you could watch Venus for a long enough time. Now, you'd have to be watching it for long periods of time to be able to see this. I'll slow it down a bit. But it's interesting, the path of Venus, or the phases of Venus that would be predicted by this. Okay, let's move on to the next model. The Ptolemaic model was lost to European civilization after the collapse of the Roman Empire, but other cultures in the world kind of kept it alive in India and in the Arabian countries. They hung on to it, translated it into their own languages, sometimes modified things a little bit. In the early years of the Renaissance, or shortly after 1200 AD, it worked its way back into European countries. People started copying it, spreading it around. It made its way back there. Eventually, someone comes along, Nicholas Copernicus, who proposes a different model of the universe. He lived from 1473 to 1543. He was a canon of the Catholic Church. That's like an administrative position, a clerical position kind of thing. Not clerical, he actually had administrative powers. He would be responsible for seeing that taxes were collected in some area. In those years, the Catholic Church was the government in many places in Europe, and so they would have to collect taxes, provide for the defense of areas from marauding knights or something like that, have some way of delivering charity to the poor, all those sorts of things. His great work, called De Revolutionibus, it had a longer title than that, but De Revolutionibus is good enough. It was published in 1543. You may notice that there's a coincident date with the top line and that bottom line there. He may not have been aware of his book's publication. I bought a new to me book on Copernicus. It was actually written in about 1970, I think. The author of this book I'll mention a bit later. You'll see his name here. Copernicus may not have been aware of the publication. When the last parts of it were delivered to where he was living and working at the time, he had had a cerebral hemorrhage a few months before it arrived, and one of his co-workers, in a letter to their local bishop, said his memory and mental powers had abandoned him. But here's the Copernican model in the simplified version. He made it more complicated later, and I'll mention those things, but it has the sun at the center. It'll look familiar. It's got Mercury, Venus, Earth, the Moon, Mars, Jupiter, and Saturn. It had the approximate correct spacing for these planets. This is a simplified version of it, where the planets seem to increase in orbital diameter in a regular way, but Copernicus's model wasn't that simple. Still, they're all circles, but it's got the sun at the center. We call that heliocentric. Helios is an ancient word for the sun. It had circular orbit. It had a simple explanation for retrograde motion. Let's look at another computer animation for that. Here we have the sun at the center. We have an observer planet, which will be Earth. We'll have a target planet, which for this one will be Mars. It's got, we haven't learned what these are yet, but an AU is an astronomical unit. It happens to be the diameter or the radius of Earth's orbit, pretty close to it. And then Mars' orbit has an orbital radius of about 2.4 astronomical units. I may slow down the animation a little bit for starters. And again, you can watch the motion up here, or you can watch the apparent motion of the planet against the background stars as they're traveling around the center of this thing. Now, I maybe slowed it down way too much, but you can see that the sun has a pretty constant motion against the background stars. Now, Earth is going to be moving into such a position that Mars will be behind the sun at this time, and the sun catches up to and passes Mars. I'll speed this up a bit so you don't fall asleep. we're soon going to have, I paused it here, we're soon going to have Earth catching up to and passing Mars in its orbit. And watch the bottom as that's occurring. Mars stops, moves backward for a time, and then moves forward. And that is the simple explanation for retrograde motion. Copernicus said, the nearer a planet is to the sun, the faster it travels. And just by saying that, it takes care of explaining the retrograde motion of Mars, Jupiter, and Saturn. It also explains the weird behavior of Mercury and Venus that we can see. Not perfectly, however. So that's something that we'll have to concern ourselves with. Let's have it catch up, Earth catch up again, and then I'll slow things way down. Okay, Mars appears to be frozen in space, but as Earth passes it, it looks like it moves backwards for a time against the background stars. At some point it freezes in space again and then starts going forward or eastward against the background stars again. So that's the Copernican explanation for retrograde motion. Simple explanation. Accuracy, well, for starters, the Copernican model was hardly any better than the old Ptolemaic model, which over the years had gotten less and less accurate as far as predicting planetary positions. People had tried to update it from time to time, but still it suffered from that, and Copernicus's model did as well. And so, to improve the accuracy of his model, he made it more complicated. He added epicycles for the planets, and it only slightly improved things. If he'd spent enough time on it, he might have narrowed it down, made it a bit more accurate, but the problem was you're trying to say that things are traveling in circular orbits, and they're not doing that. So that's just the way it goes. By the way, if you like reading about history, here's some books that I've read dealing with this era. Galileo's Daughter by Davis Sobel. Interestingly, Galileo and one of his daughters, Maria Celeste, we'll learn about her or him later, but she appeared to have been his intellectual equal, and they wrote letters back and forth for many years. Galileo's copies of those letters were saved, but they'd never been translated to English until just the first part of the 2000s when Davis Sobel did that. Letters to My Father is the letters themselves. Galileo's Daughter is in large part a biography of Galileo. The Sleepwalkers by Arthur Koestler is kind of a complete history. It's tough going. It's not a really exciting book. A book I really enjoyed was The Great Copernicus Chase by Owen Gingerich, and The Book Nobody Read by Owen Gingerich, and another Coming of Age in the Milky Way by Timothy Ferris. I really enjoyed that last book. I read it close to 30 years ago, and I've reread it 2 times since then. He has a way with words in writing about history. Okay, next up will be Galileo. Galileo was the big supporter of Copernicus in the generations after Copernicus died.